I'm audible.
Yes, sir.
Okay. You have the two options now. One, if you want to prepare for the quiz for today, I can take the class after the quiz. Or is okay, we are prepared already, sir. You can continue, means I can continue. What is your suggestion?
Sir, continue.
Yeah. So in this class, we will discuss about the instructions which are available for accessing the memory, different types of instructions what are available for accessing the memory, different addressing modes related to the memory, how do we access the multiple things. So we'll just discuss about these things in detail in this class, and also some other instructions which the move related, that the multiplication related also we'll discuss it for a moment. One moment. Now, so before we will go to the memory related instruction, we will finish one or two multiplication related instructions which we have not covered. So, and then continue with here. Now, so we know that there is no division instruction is provided. The division instruction is provided. So we have used successive subtraction. Similarly, there are two instructions are provided that is called as a multiplier. The block is there. So the multiplier block is there in the architecture of an ARM core, which supports two instructions of multiplication. One is mul instruction, other is called a multiplication with an accumulator. So what is a multiplication instruction will do? So there are three operands are there. So source, operand 1, operand 2, multiply together, and answer is stored in a destination operand. We will take an example. Now I taken 2 and 3. I'll perform the multiplication of 2 and 3. 6 should be there here in the register R0. So I just taken multiplication of two numbers. So R1 and R2, 2 and 3 is loaded. If you just look at 2 and 3 is loaded. Now the 6 should be there in the answer in the this one. 6 is loaded here. So this is the how multiplication is performed. So let's now continue the discussion from here only. The other type of instruction that is called as a MLA, multiply and accumulate. What is this instruction? We'll do it. This instruction will have three operands, operand 1, operand 2, and operand 3. Operand 1 and 2 is multiplied together, and then operand 3, which is added to the here, and then we'll put it here. It's like a whatever the previous multiplication you have done it, that you are accumulating into the current multiplication. That's why it's called as a multiply and accumulate. So we will see in this case what will happen. Now I have already multiplied R1 and R2. The answer is there in the R0. Again, I'm performing another operation. Now, what is MLA will do it? Multiply R1 and R2. In this case, 2 and 3, it becomes 6. Then it will add to the R3. So R3 is 4. That means that 6 plus 3, 6 plus 4 is a 10. So A should be the answer in the register here. So 2 and 3 multiplied, 2 and multiply 6 plus 4, 10 should be here. So I'll execute that instruction. You got it 10. So that's how MLA instruction is going to the work here. Now I have taken an example how to compute the factorial of a number using this concept here. There is a one disadvantage here that you have to remember here when you do a multiplication instruction. So you should keep in mind, for example, I want to multiply R1 and R2, keep the answer in the R1 itself. It is not possible. It's not allowed. So that means that I want to multiply R1 and R2. The answer, whatever I get from R1 or 2, I have to keep in the R1 itself. So this we do in the add, subtract, and everything. Here it's not possible. See that? Now what is an error it will get? It will not compile your instruction. See that an error, it says that. I mean, the register combination results in unpredicted behavior. It will not allow you to execute the instruction itself. Whereas R2 is allowed. That means that operand 1 is not allowed. Say R2 is allowed. If I keep it like that, this is allowed. This is allowed. But R1 is not allowed. So you should be very careful here when you do this one. So that's why I have taken here different register. So that means that the operand 1 cannot be a destination operand. That you remember that if you keep it, it will not allow you to execute it. Now let's write a program for the factorial of a number using a multiplication. This is one example program, application of a multiplication. Let's say the number whose factorial I want to find out. I've just stored in a register called R0. One moment. So I have stored the number to be whose factorial is in 5. The first number is a 1. I keep multiplying the R0 to the R1. Now R1 and R0 are multiplied. That is R0 I am multiplying to the R1. First 5, then 4, like this I will multiply, then 3, 2, like that. If R1 is allowed, I could have written here R1 and I could have finished my program. This statement would have been common. It's not required. So if this was allowed, since this is not allowed, now what I have to do is, so I cannot put R1 here. So I've just taken temporarily another register called R2. After the multiplication, I'm keeping R2 back to the R1. After the multiplication, I'm putting R2 to the R1 because it's a destination. R1 is not allowed. So what I'm doing, I'm subtracting the R0 every time until it becomes 0. If not equal, I'll continue. So I'll keep multiplying. So the reduced value of R0, 5, 4, 3, 2, 1 to the R1. So which holds the R1 holds the previous accumulated multiplication. So you can simplify this program. Also, you can just try with MLA also. See that you can able to simplify this system. This is one of the method. So I'll just return it. So now we'll compile this and we will see that 78 is the hexadecimal value of 5 factorial. So we will run this program and see that how does it work. 2, 3, 4. This is finished. Now I'll come here. 5. I'll execute the program. Where is my answer? So my answer is in the R2 register. My answer should be in the R2 register at the end of the program. So I'll run at a short. Then I'll stop it. So you can see that R1 and R2 both contain the 78. 78 is a hexadecimal equivalent to the 5 factorial. So this is how you can use a multiplication instruction. So this is about the information about how you can use the multiplication instruction and MLA instruction in your program to implement your expressions. So only thing is in both the cases, so RM cannot be RD, operand 1 cannot be the destination. That you remember that and you can do the program. You may ask the question, sir, if I multiply, what is the size of the number? 2 numbers I can multiply. Yes, the size of the numbers you can multiply is 32-bit and 32-bit. By chance, if I multiply 32-bit, 32 full, my answer is what? More than 32-bit. Then you're losing the answer. Yes, you're losing the answer if the numbers are larger. So for that, some of the codes provide one more instruction. So that instruction, I will stop sharing and share the PPT also together. Now, could you see the PPT? Can you see the PPT now?
Yes, sir.
Yeah. So now you can look at the multiplication instruction. To support the larger number multiplication, MULL is provided. So MULL is a 32-bit into 32-bit, which gives a 64-bit answer. So what is the way you have to do it? Here also same thing. See, there are two operands you have to multiply. That is called as operand 1 and operand 2, RM into RS. But the answer is 64-bit. So you should indicate what are the two registers where you are storing the partial answer. So the first operand, that first destination will have destination answer is stored in two registers, the lower and the higher portion. So the lower register will store the 32-bit number. The upper register store the 32-bit number. So total my answer is what? 64-bit. Total answer will be 64-bit. That will be generated by when large 32-bit numbers are multiplied. This is one of the way. This multiplication, whatever the large, that is a 64-bit holding answer multiplications will be of two types, unsigned also, signed also. So you can just say U means unsigned. By default, it will be unsigned. But you have to check it. That is, you have to check it. I'm not sure. You have to check it. So there is a S means it's a signed one. You have to type it. So these are the two instructions are provided: signed and unsigned multiplication of large numbers. So In both the cases, you can see that this one is MLA, similar to the earlier one. The other is a multiplication. So both support signed and unsigned multiplication. This is how you can do it. For multiplication instruction also, you can include a condition codes. Like any other arithmetic operation, you can include a condition code and yes for updating the flags only. So it is not a one clock cycle instruction. You should always remember, most of the instruction I said, it's always one clock cycle instruction. Multiplication is not like that. For ARM 70D MI, that is a LPC 2148, it takes around 2 to 5 cycles on ARM 72 MI. So you should also remember that variable number of clock cycles for some process which implement early termination, the multiply is faster for smaller values in RS. So if the values are more, it will take a more number of clock cycle. So it also says that ARM 72D MI use 8-bit Booth's algorithm, which take 1 cycle for each byte in RS, terminates when rest of the RS is all zeros and are all ones. That means that so when the number is smaller, what you are multiplying, it completes in a faster cycle. It completes in a less number of cycles. When the number is larger, it takes a more number of clock cycles. So MUL and MLA does not need signed or unsigned specified, because they return the low 32-bit of the result, which is same whether same whatever the sign of the arguments. So that means that MUL and MULA does not require specifying U or yes. Why? Means they don't need signed or unsigned specified, because they return the low 32-bit of the result, which is same whatever the sign of the arguments. So this is about the multiplication, about the support provided in the ARM. Okay. So this is some of the other things. Okay. So just remember only this much. What is you have to remember? You don't require to remember. You don't remember all this information. It's not required, because this is for a different types of course. You have to just remember that MUL and MUL instruction. If you remember, it's good enough. And just remember that MULL and MLAL for large number, it's available. And you have to check that whether does it support the core. It is not supporting here in this architecture. You have to just check it then. Okay, so for this architecture, that's why you don't require to study for this, for the exam also. For this architecture, that is LPC 2148, that is a ARM 70D MI, whatever we are studying. So this is not supported. This is not supported. Say that unknown opcode, MULL, expecting opcode or macro. So it's not supported. So as I've shown, we will be working only on MUL and MLA. This is not supported for this core, whatever we are working. Now, so this completes about the arithmetic instructions, whatever we have studied. So only thing is, some of the instructions you have to see, go through that in this slide. So what are the things? For example, we have not covered 1 or 2 instructions. Means CMN. Compare is operand 1 minus operand 2. CMN is the opposite of that. So operand 1 plus operand 2, but result is not written. So this you can just try whether this is core supports. This one you can try CMN. And you have to try the subtraction with the carry. Okay, of course. Reverse subtraction, you have to try it. So subtraction, we did it. Operand 1 minus 2. Reverse subtraction, you try it. Operand 2 minus operand 1. That is the one thing you have to try it. So reverse subtraction and the CMN instructions, you try on your own. So otherwise, we have completed almost all these instructions. Okay. So now we will go to the load and store concept of instructions. So now we will study about the other types of instructions, what is available for storing and loading. Now, so now we will focus completely in the next 10-15 minutes on the memory related addressing modes. So what are the memory related addressing modes are available and what is their meanings and everything, we will study that. Already we have used some of these addressing modes, but we'll just classify them. What are the names and other things are there. So there's one more fundamental notes is there. I'll just circulate you today this information. So these are the addressing modes supported by. These are the addressing mode supported by for the memory. So what are that? So register indirect, the first one, base offset, base index, and the based scale index. These are the 4 addressing modes which are available to access the memory along with an LDR and a STR instructions. We have studied this many times. This we have used. It's called as register indirect. If an example is to be asked, register indirect means what? One of the registers you're using to hold the pointer and access the memory. This we have understood that. Base offset also we have understood that. What is the base offset? That means that so you are adding some offset value to the base register. So if there is only one register you use it, correct? We call it that is a base register. So offset value is added and the total sum will be prepared. That is an address from where you are going to get the data into register R1. This is called base offset. The third is called as the base index register. So what is the meaning of the base index register? It is used to access different data structures. For example, you use one of the register to indicate the matrix row. Another you can indicate the matrix column. That means that whenever you want to access the data structure like matrices, you require 2 pointers required. One pointer pointing to the rows, other pointer pointing to the columns. So you can always use this type of data structure. So we will do one example of the base index and then we'll come back to the other one. We will just see that. So now what I'll do is I'll just see the base index first and come back. Okay. So look at this instruction base index, and I have stored some numbers 1, 2, 3, 4, 5, 6 in the memory. So I'm not accessing the matrix here. I'm accessing like an array. I'm accessing like an array, single dimensional array. So I've just created a single dimensional array with some 6 elements. So I have set up a base pointer. What is a base pointer for me in this instance? The address of the memory location called data. Data is a base pointer. I load the base pointer. Now R0 is a base pointer for me. So now, to access the different memory locations, I use another register called R1. So it's an index register for me. So R0 I'm using as a base register. R1 I'm using as an index register. To start with, I'll make it 0 index register. Now this is a based index addressing. So R0 address, contents of R0 plus contents of R1, they will be added together and the effective address will be prepared. Effective address is always the final address which is used to access your memory location. That's called effective address. We use a word. So R0 is nothing but what? The data. So R1 to start with a 0 so that it is referring to what? So the 1 I'll be loading into R2. So when the program runs first time, I'm getting the 1 into the R2. Next, what I'll do is I'll increment the index register by pointing to the next memory location. Since the 4 bytes are required for one memory location, I'll increment the R1 to point to the next memory location. So that's why I'm incrementing index register. Now, so I'll repeat the program again. Second time, I'll be getting what number 2 into the memory location. That is a register R2. I'm not doing anything. I'm just discarding the data. I'm just getting the data into the core. So third time, I'm getting a 3, 4, 5, 6 like that. That means that, so this technique allows us to go through the single dimensional array and access all the elements. You can use the same technique to access the different elements of a matrix also. In that case, matrix, what you do, you not only increment the R1, you should also increment the R0 also properly. Depends upon the number of elements you have in a one row. So by incrementing R0 and R1 appropriately, you can access the different elements of a matrix, or by keeping the R0 constant, you can access the different elements in a single dimensional array. We will just run this program and see the value. So we will be keep watching the register called R2 here continuously. So as I run the program, R2 will be fetching the data one by one. So I'll execute the instruction. So keep looking at the R2 register. So now R2 got the first element. So look at that R0. So R0 is nothing but what? 20. So 20 means that is the data. What is the available there? Your data. Okay. So that is from the 20th memory location, 1, 2, 3, 4 data is available. So the base pointer R0 will point to the 20, and the R1 keeps incrementing, accessing the next location. Now look at the R1, it becomes 0 now. So now I'll increment, R1 becomes a 4, the index register. Now I'll get the second number. So 2 number, I got it. So similarly, if you watch R2, so I'm getting 2, 3, so 4, so 5, and the 6. So this is the meaning of how you can access based index addressing mode to access the different data in a single dimensional array matrix access. So whenever you want to implement a matrix in the low level or assembly language programming, this is how the techniques used. So now we have understood that uh, how base index addressing mode is going to work with an example. Now, other is a based scaled index. This is similar to this one only. Only thing is you are using the R2 value, that is operand 2, that is index register contents. Then applying that is what is called as you're shifting the R2 value as per the whatever the indications given here in the next shifter operand, and then you're using for the calculation of effective address. So R2 is shifted left by 2 and then added to the R0, and then effective address will be calculated. It's called as based scaled indexed. Why scaled? Because you're multiplying the index register by 2 or dividing that by 2. You're shifting to the left or to the right. So these are the 4 addressing modes supported for accessing the memory location. Repeat, one is a register indirect, other is a base offset, other is a base index, other is a based scaled index. So these are the 4 addressing modes are available for us to access the memory. So now we have understood all the 4 types. Now, there's one more concept is there in the memory accessing. So we will just study that concept now. So what is called as every instruction, whatever you learned till now, str, ltr, there are 2 types of indexing will be there. That is accessing the memory location when there is another operand, when either index or offset is specified. How do you access that? How do you specify that one? So that is using what is called as pre-indexed and a post-indexed. So in case of a pre-index, let's go to the pre-index. In case of pre-index, what we do is if I give an instruction like str, r0, r1, 12, that means that as we already discussed, the contents, am I audible?
Yes, sir.
Yeah. Yes, sir. Okay. In pre-index, what we are doing is that is whenever I put in the brackets, we already know that this is we have used number of times. The R1 is added together and we'll do it. That means that so it's a pre-indexed in the sense the value whatever you specify within the bracket is added to. In this case, they have taken example 200. Let's say R1 is equal to 200. So 12 offset is indicated. So offset is added, and then you are referring to that data, the location. There you are storing your number. That is 5 is stored here. That is called pre-indexed. In a pre-index, the option is there. That means that here the value of R1 is not changed. If you want to change the value of R1 after you access the data, you can use what is called exclamatory symbol after that. In exclamatory symbol, what will happen? After you execute the instruction, the base register, the R1 is also value will be changed. Otherwise, the value will not be changed. It's called pre-indexing. So we will understand with an example and then continue there. So we will just work with an example here. So anyway, this data is not required here in this case. Okay. Now I have taken 400 is a address. So this is called as, so I will use it first, pre-index hash 12, and then I'll store it. So I'll compile my program. Okay, I'll execute this program. Okay, I'll just go to the memory location 400. Now this is a base pointer I've just specified. So this is a offset value is a 12 I've indicated, correct now. So when you add R0 to 12, the effective location where you're storing is what? So 12 means what? 3 numbers you can store. That is after the, that is the 4th number basically. 12 by 4 means 3. That is after the 3 numbers. So 0, 1, 2, 3, 4, 5, 6, like if you continue like this, correct now. So after the 3 numbers, this number will be stored. So it is a C, the location C, it will be stored. It will start storing it. 5. So we'll execute this instruction. So now this instruction is going to execute. Now look at the value of R0. R0 becomes 400. So base point is pointing to what? So it's pointing to 400. Now we'll execute that instruction. Now it is going storing here 5 because 12 bytes after the 12 bytes. So after the 12 bytes, you leave the 12 bytes. So that is after 3 numbers. This is the after 12 bytes will be stored here. What is the number stored? 5. So this is called pre-indexing. Pre-indexing because why? So before executing the program itself, not after executing, before executing only the 12 is added to the base pointer, and then that address will be used to for storing the value. Same thing you can apply for LDR also. Now one variation for this, we have used this instruction. One variation will do it. Now I'll put an exclamatory symbol after that. So that means that whenever I use an exclamatory symbol, it's used only for pre-indexing. You should remember that it's used only for pre-indexing. So whenever you use an exclamatory symbol, what will happen is after you perform the operation as it is, no changes in the operation, the value of R0 is getting updated. That is, base pointer gets updated with a new value. Base pointer will be updated with the effective address. What is an effective address? R0 plus 12 is an effective address which you used to store something in a memory. That effective address will be updated into the R0 register. So it should be C. So 4000 C should be there in the R0. So we will run this and we will just verify how does it work. So now, so look at the, before I execute the instruction, now see that R0 value. What is R0? 400 is there now. Now I'm executing that instruction now. So again, exactly at the 400C, the 5 will be stored. But the value of R0 is still what? R0 is still 400. I'll execute that instruction now. See that now. The 5 is stored here, but look at the R0 now. So R0 has been changed. 4000C. That is new effective address which has been calculated. So at the time of execution instruction will be updated in the base register. This is called as updating the base register. So this concept you can always use it. Depends upon how you implement your pointers and incrementing the pointers. Based on that, you can able to use them. So now we have understood pre-indexed addressing mode. We have understood pre-indexed with an option called base register updation. Also, we can able to use it. Now we will understand what is the concept of post-indexed. So in case of a post-index, so we will go with the instruction. Now what we will do is I will remove the inside. I will put it outside. Now we have also this also we have used in the program 1 or 2 times. So this is called post-index. In case of post-index, so what I am doing is I am updating the contents of R0. Now what will happen is the first R0 will be used to access the memory location. One moment. I'll just. Okay, so here the contents of R0 will be used first to access the memory location, store the value of R2. Then R0 will be updated. How much R0 will be updated? R0 is equal to R0 plus 12. So there is no question of exclamatory symbol is required here because anyway it's getting updated. It's not required here because why? Anyway it's getting updated. So that exclamatory symbol is used only in pre-indexing. You should remember that it's not required in the post-indexing. So now what will happen here? It's called post-index because why? The value, whatever the index value specified, the displacement you are specifying, you are updating only after the accessing a memory location. Now look at here. Now the 5 will be stored here. The 5 will be stored in the memory location pointed by R0. Now what is the value of R0? So R0 is nothing but 400. So 5 is stored here. So 5 is stored here. See, the 5 has got stored here. Now after the instruction is executed, go and verify the R0. So R0 has changed to 400C. So this is how you have to see that you are in C language. We use it's very important plus where to use it. I can use a pre-increment and also I can use a post increment. When I give any C statement, correct, you should be very careful. If I use a post increment, yes or no, you can always go for this type of addressing mode. You can go for it. If I give a C statement, pre-increment plus, I'll give it. Then you have to go for what? Pre-increment. So you can you can implement any pointer, pre-increment pointer or a post-increment pointer using this type of addressing modes. So this completes the basic LDR STR instruction with a different addressing modes. So now these are the addressing modes we have studied. So these are the 4 addressing modes are there, and it supports in all of these addressing modes supports what's called as a pre-indexing and a post-indexing also is supported. So now it completes that one. Now we will study what is called as multiple register load and store. So this completes the same thing, whatever I shown in the example, the same thing is there here. So it's a post-indexed and this is a pre-indexed. So you can always, when I say, if you just look at this, are you able to see this? This example, see example?
Yes, sir.
Yeah, you look at this example. If this example is given like this, and you're supposed to write the assembly code, you have to write like that. Integer star pointer, x star pointer plus plus. How we can implement this one? So R1 hash 4 into the R0. R0 is an X register. R1 is the pointer. So like this in the quiz, what we do, we can give an example like this, and we will tell you R0 is this register and X is register. We will give a 4 option, which is a correct instruction for this. You can write like this. So always remember, don't get confused. Always remember that. So when you write number after the register, it's called post indexed. When you include the number, that is a displacement or offset inside the brackets, it's a pre-indexed. So in case of only pre-indexed, the exclamatory symbol we use it. In post-indexed, we don't use an exclamatory symbol. So if you remember that one, I don't think much difficulty will be there in answering memory-related questions. Now we will study what is called LDM and STM instructions. So till now, whatever we have studied, all these instructions, it is related to the single memory location. That means that I can access a single memory from the memory location, bring it to the core, or I can put the content of one register into the memory location, one location. But there are many cases out there. You want to get, let's say, 10 numbers from memory, load into all the registers, R0 to R9, perform certain operation, put my answer back into the memory. So it is very easy if they provide a single instruction which can fetch multiple memory locations and put into all the registers, because you have many registers are there. If registers are only 4 or 5 is there, this instruction would not have been required. Since there are about 16 registers are there, it is better to have this instruction support is required. So LDM. So as the name says, load the multiple registers. Where do you want to load into this register? Whenever you want to use this instruction, there are 2 things are there. One is, as the name indicates, you're loading from where? From memory, loading from a memory. So whenever you use an LDR STR instruction, the way you specify the pointer, the way you specify the registers were little different. So in LDR register, it is different. In LDM and STM, it's a little different. So don't get confused with the LDR and STR for a moment. Keep it aside. Keep it LDR and STR for a moment aside. Now, there are 2 things is required in a LDM instruction. One is what? You are loading the data, multiple data from the memory location. The question comes, when I want to load multiple memory locations, from which memory location I should at least indicate the starting address. So that is a starting address. So I'll say the first what is required, starting address is required. So I can just say R0, because it's understood, it's instruction LDR, LDM R0. Now, before that, I will load into some number here. I will load into some number R0, hash datas. I will store the datas in the memory. DCV 1, 2, 3, 4, 5. Let's say 5 numbers are there. Now I want to load into from the memory location pointed by R0. One data is given. Now, how do you specify the different where it has to be loaded? Because you are getting the data from where? Memory. How many data you are getting? Multiple data you are getting from memory. How much you require? Is it 4? Is it 5? Is it 6? It is not depends upon the programmer requirement. The programmer can specify. For example, I want to get 3 numbers from the memory at a shot. So that means that you have to take a decision. So now 3 is required. 3 is decided. You have decided to get 3 from the memory. The next question is the 3, when you bring that from the memory, starting from a data which is indicated by R0, where do you put the 3 numbers? Where is a place inside the core? Only the registers. What registers you have to put it? You should indicate it. For example, I want to load them into R1. I want to load them into R3. I want to load them into R5. That means that as a programmer, you should take a decision. I want to load from the memory because this indicates 3 numbers, which is starting from the data, which is indicated by a pointer called R0. You have to indicate like that. Now, coming back to the PPT, just look at that. So what I'm doing here, I'm loading into memory, loading from the memory location. How many numbers? So R0, R1, and to R4. So we'll go back to here. So I'm just loading into some of the registers I've taken here. R1, R3, R5, I've just taken it. So now we will see that. How does it work? Now I'll compile my program. So there are 2 warnings there, and we'll see that what is the first. No section matches. Note. Okay. Added 3 bytes of padding at address 0x11. Okay. 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 So it's alignment. It's related to the alignment. We will discuss that. What is that alignment later? Now, so now I will execute the first instruction. I'll go to the memory. So your memory is 0C. I will just check the numbers. So 0C, enter the numbers. Now 1, 2, 3, 4. Oh, D. Sorry. Okay. I have given DCB. So it's allocated like a bytes. So it should be DCD. It should be okay. Okay. That is why it's given a padding byte. One more warning. It's given for a padding bytes. Okay. So now I'll execute this program. So now the numbers are there. 1, 2, 3, 4 numbers are there. Now look at the register. R1 0, R3 0, R4 0. Now I am loading all these numbers. Now what I supposed to get? So 1 should come to R1, 2 should come to R3, 3 should come to R5. So I'll execute it. Now all are empty now. I'll execute the program. See that R1, 1 you got it. R3 you got the second number. R5 you got the third number. That means that in a single shot, I am able to get multiple memory locations into multiple registers. So this is the meaning of what is called LDM, loading. So loading. See the destination and the source is a reverse compared to LDR instruction. Yes or no? In LDR, so this is the source, this is the destination. We have reversed it. You should always remember that LDM STM is always opposite of LDR STR when you specifying the source and destinations. So now you got. So now one small variation I'll do it and just ask you what to do it. Now I have replaced like this. Now can you tell me now? Can you tell me now what is the value loaded into R3? See, now I have changed this one. Now when I execute this program, now what is the value to be loaded into the R3? Generally what we expect, so we expect 1 should go to R3 because first register, 2 should go to R1, 3 should go to R5 because it goes in order. No, not at all. It will not do. Whatever the order you specify, it will arrange it in an incrementing order, increasing order, and then only it loads the number. So it will not load 1 into R3. It will still load 1 into R1. We will verify this one. So now I'll compile my program. Now I'll compile my program. Just see that now I got the pointer. All my numbers are there. Now after the execution, 1 should go to R3 as per our logic, as per the indication here. But it will not happen. So now I finished instruction. See that still the 1 has gone to R1. The 2 has gone to here. That means that whatever the order you specify the register, it is always arranged in ascending order and then it will only do it. So this is how the LDM instruction is going to work, the multiple register. Now similarly opposite of that LDM, that STM, we will see that with the help of the PPT. Now, so before we go to the other one, STM instruction, we will understand, look at only LDM instruction. LDM instruction supports 4 addressing modes. That means that after LDM, you can write, these are the 4 options you can able to write, IA, IB. See, after this, you can write increment after increment before, decrement after, decrement before. Sorry, decrement before. That means that, so apart from the conditional code, whatever you are allowed to do it, that is conditional code, I can always write it. Apart from the conditional codes, you can now specify addressing mode for the load and store instructions for multiple registers or multiple memory locations. What are the 4 addressing modes are there? So one is increment after IA. That means that, so which is the first memory location I'm going to access? What is then specified in R0? Use the first memory location to get the first number, that is 1, and then increment R0 to point to the next number, then increment, like that will go. That means that increment after, that means that first use the memory address specified in R0, then afterwards you increment it. That's called increment after. So there's an option called increment before is there. Increment before means, so that means that before accessing you increment it. You access before accessing, you increment it first. So in this case, what it will go to the 2 and then access that memory location. We will see an example. So by default, increment A was there. By default, increment A is a normal. Increment A is a normal. There is no difference is there. Because even if you don't specify, you just look at it. If I don't specify anything, by default, always it's an increment after. You can just see that in the disassembly window. So look at the disassembly window now for a moment. Look at the disassembly window. See, look at that here. That means that even though I have written LDM instruction, automatically it has taken what? LDM IA is taken. But that means that by default, if you don't indicate anything, it is equal to what? IA. That is increment after only. That's how we were working it now. Till now, when I say LDM, it's nothing but what? LDM IA. So it increments after using the first address. Now we will do the other one. LDM increment before, IB, increment before. Now we will compile this program. Now we will see that what will happen. Now, so I'll execute the first instruction. All my numbers are there, 1, 2, 3, 4 is there. I'll execute the first instruction. That is R0 is pointed to the numbers wherever there, that is a 0C. So now look at here. LDM IB is there. Now what will happen? We'll see that. Now, what is the R0 is pointing? R0 is pointing now to the first number, because look at that. R0 is what? 00C. At 00, the first number is there. But increment before is there. Since increment before is there, what will happen? R0 will be incremented. So before using it. So before using it means, what is the first number I'm supposed to get? I'll execute this instruction. Now see that 2, 3, 4, I got it. I did not got 1, 2, 3, 4. I got what? 2, 3, 4. Because why? It is incremented before accessing it. So R0, whatever the value is there, that will be incremented first, so that it will point to the second. So I'll access the 2 and then 3, 4 will be accessed. So you have to remember that. So if I give this code in the quiz, I'll ask what is the value of R3, R1, R3, R5. You should look at what is an addressing mode you're using it. In a normal one, you access 1, 2, 3. If you use IB, you access what? 2, 3, 4. So that you have to understand. So now, so we will understand one more addressing mode. Now, so that is called decrement addressing mode and decrement before that one. Let's look at here. Let's see the decrement address, decrement after. That means that decrement after means first you use the address pointed by the base pointer, whatever the register you're using to point to memory location, and then it will be decremented. So whatever the value you have, R4, R1, R0, see the arrangement is different now. Actually, we expect that it should be R0. We expect should be R1, R4, because they have used here R0, R1, for example. So R0, 1, 4. Here also 1, 4, it's correct, because 1 after that. So here we expect 0, 1, 4. No, it's not like that. Always ascending memory address order is used. Always for storing or accessing, ascending memory address is used. So whenever you use a decrement, now what will happen? You are accessing the memory from higher address to lower address. But how the memory organized always from incrementing address. That is, if this is the first address, this is the last address. So that means that since there is a rule is there, always ascending memory address to be taken. Now, whatever the registers you specify, the bottom address, lowest address is what? The first register. The next is that, and the next is that. That means that the lowest address will be accessed first, and then the next one, and then the next one. So we will see an example here. Now in this case, we will see program an example. Now, now since it's a decrementing, what I'm going to do is I can able to put my datas. I can able to put my datas. 1, 2, 3. I'll put some datas here. Now 3 datas. So I'll create one more data. Datas 2 DCD, and then 4, 5, 6. I given it now. So now I will point to datas 2. Now what will happen? R0 is pointing to where? The 4. R0 is pointing to the 4 here now. So 4 means the R0 is pointing to here now. Now I'll say decrement after. I'll just use it. Now guess what is the result you're going to get now. So now I have made the data into 2 portions. So one is 1, 2, 3. Other is a 4, 5, 6. I made it. So since it decrements, I'm just split into 2 portions. Datas 2 I have initialized to R0. Now we'll execute this instruction. See, guess what will happen. So to avoid your confusion, I'll take the register in the same order, in the incrementing order. So to avoid little confusion. So R3. So this is R1, R3, R5. Now see that. Now I want to find out what is your answer. You should be able to tell me the answer. Tell me the answer for R1 equals, then R2 equals, sorry, R3 equals, R5 equals, like quiz questions. If they ask like this, what is your answer? Guess. I'll compile this program. So I'll run this program. So I want to find out what is the value of R1, R3, R5. Now look at R0. What is the value of R0? Now 18. R0, 18. So 1, 2, 3, 4, 5, 6. So 18 means this address. 18 means this address, because if you can count it, C, D, E, F, 10, 11, 12, 13, 14, 15, 16, 17, 18. That means that now R0 is pointing to what? 4, 5, 6. It's pointing to 4, 5, 6. Exactly 18 is there now. Now load from the memory with addressing mode decrement address. Decrement after means whatever it is pointing now, it will access first. So what is the value it is going to access? 4 it's going to access and put into R1. We will see that what will happen. So I'll execute that one now. So it's finished instruction. Now check that. So R1 contains how much value? 2, 3, and 4. Because why? The lowest, if you look at this PPT, the lowest address, the lowest order of the address among these locations, that is, you have indicated one address. From there, 3 addresses are used. What is the lowest address? The one which is the first data. So in this, it'll go back to here. So which is the lower address among these locations? The 1 is the lower address. Look at that. This is C. After that, what? C, D, E, F. Then what? 1, 0. That means that this is the lowest address. If you keep looking at these numbers, the number which has got a lowest address is what? 1. So that is taken there. That is 1. That is a 1. Next lower address is what? The 2. Next lower, sorry. After that, next address is what? For the 2, then 3, and 4, 5, 6. Now, what are the 3 numbers I'm interested in this way? Since it's a decrement after, I'll use this number also. 4 is used, 3 is also used, and 2 is used. So 4, 2, 4, 3, and 2. These are the numbers I'm going to use. Because I am pointing to the datas 2. The wherever you're pointing, that also I'll be using, because I'm decrementing the pointer after that. So I'll be using 432. In this 432, so which will be the lower address in the 432? 2, 3, 4. Lower address is 2. So that will be taken 2. And which is the lower register here now? Lower register is R1. So always remember that lower address go to the lower register. Lower memory address always go to the lower register. This is the principle. So next lower address is what? After the 2, that is a 3. Among the 3 and 4, next lower address 3. 3 has gone to here and 4 has gone to here. So this is what you have to remember. It's very clearly. Always rule. What is the rule? Lower memory address should go to the lower register. So only thing is whether you start from 4, you have to count, or 3, 2, 1, you have to count. That depends upon whether you use decrement after or decrement before. Now I'll change that one. Now I have just found out the answer for this case. So what was answer? So 2, then 3, and then the 4. This is the answer. So this is the answer for this case. Now we'll change it. That is, am I audible? Am I audible?
Yes, sir.
Yeah. Now I'll change decrement before. Decrement before. So now I'll remove the answer and I'll verify what was an answer. Decrement before. Now I'll compile my program. So now you can clearly guess because you know the rules of the game. So now I will not execute. I'll just stop here. Now LDR R0 is equal to data 2. That is R0 is pointing to what? So 18. That means that 4, 5, 6. It's pointing to the number 4. Now decrement before. The decrement before means it will not access 4. It will decrement and then access. Then it will go to the 3. So what are the three numbers it will access? 3, 2, 1. Now which is the lowest memory location? 1. Then the 2, 3. So lowest memory location go to the lower register. That is what? R1. So 1 should go to R1, 2 should go to R3, 3 should go to R5. We will execute and see that. See that 1, 2, 3. We got it. So this is how you have to understand the working of. So I'll just write the answers here. So in this case, it's a 1. So it is a 2, and it is case of a 3. So this completes discussion about same is applicable for store also. Same is applicable for a store also. You can try the store. Only in case of a load, what we do, we get multiple locations of memory into multiple registers. In case of store, what we do, multiple registers of the core will be pushed into the memory location. Concept is always what? Lower memory to lower register. Always remember that. And register should always start from where? Using in the when they indicate a set of register, always start from a lower register number. It will start. So we will just use the PPT and to complete that in discussion. So this is LDR, this is STR. So you should always remember that the source and destination operand positions are different compared to LDR and STR. Don't get confused. So we don't use LDM, STM anywhere in the programs. It's only for advanced logics development. When you are accessing lots of data, you'll be using it. Only for theoretical point of view, understand and execute this program and get an idea. So there is an option always an option is provided to update the base register. Whatever the register you are used here to access the memory locations, it is not getting updated. You would have seen that the value of R0 still remains there as it is not going to change. If you want to update the register, the base register, so you have to use exclamatory symbol here. So use exclamatory symbol along with the base register to update the base register value. Otherwise, it is not getting updated. So this is about the load and store instructions for accessing multiple registers under multiple memory locations. There's one more instruction is available for a swapping. So you can just specify exchanges a word or a byte between a register and a memory location. This operation cannot be interrupted, not even by a DMA. Mine use operating system semaphores. Syntax condition quote RD RM. Okay. So RN contents will be loaded into RD, and then the RM contents will be loaded into RN. Okay, RD and RM can be the same. RD and RM can be the same. You can just check this one once. So see that statement is allowed for this core. If it's unallowed, you can try that one. So you can just type that code and see that is it allowed for this core. I think it's allowed for this core. You can just try that instruction, the swap instruction. You can just try it one more time. So this completes all the slides, whatever they are related to some instruction. This is swap. There's a multiple load and register. There's a pre-index and a post-index, which is used with the LDR and a STR instructions. So this is also LDR and STR instruction. That is a 4 addressing modes, whatever it's supported here. I've used only for the words 32-bit. I have not used for byte and a half word because very rarely we use that one. Efficiency of the core is always better when used as a word access. So I'm not used any of the programs byte or a half word. So not required to just understand that it's a facility is there, but I'm not used it. So we always use LDR STR. So this is a byte and a half word. So let's not worry into that for a moment. Okay. So these are the branch instruction we have studied. So there are 3 types of branches there. Branch with a normal condition code and a label, branch with a link. You can always store the program counter into the link register so that you can come back. So these are the multiplication instruction we studied. These are the move instructions. This is the logical instructions we studied. So now this is the pseudo instructions, test equal, compare. This is pseudo operations we studied. This is the arithmetic operations, addition, subtractions, and the reverse subtractions. So these are the condition flags we have studied. So this is LDR and STR instructions. Okay. So these are the logical and arithmetical shift right, and also rotate instruction. Remember that rotate instruction left is not available. You can always use the left, implement the left using a right by using what is called 32 minus the n, whatever you want to rotate by left. So you can always implement that. These are all the instructions what we studied. These are the condition codes. Okay. So these are operating modes. So go through all these instructions. I've just circulated you this PPT also. So you see that one more set of Viva questions possible. I'll send with an answer. So you can refer that also. Okay. Any doubt is there? You can just raise your doubt. Any doubts are there?